Hello and welcome. Today we're going to learn about the distance between two parallel lines in 2D and in 3D. We will discuss case 1, which is two parallel lines in 2D. I have taken the liberty of preparing all the tools I need, so the video will be effective and not time consuming. We're beginning with L1 and L2. Their equations are given in a vector form. K and P are parameters that belong to set R. Now, in 2D scenarios, since any normal vector we draw to one line, that same normal will intersect the other line at right angles as well. There is only one family of normals, and that means all normals are in the same direction. And so as a result, we can project a vector, we'll call it AB, onto the normal vector of the two parallel lines to find the exact distance. And I'll be moving around some drawings and then we'll show some calculations as well. So first I will bring in the normal vector and a vector that is formed by a point on line 1 and a point on line 2. So we have point B is on line 1 and point A is on line 2, and the vector's direction is from A towards B. And we will see that L1 is written in a vector form, which means that will be a point B, and this will be direction vector 1, and that point here will be point A, and that will be direction vector 2. Now, since we can project here onto that one particular normal, I'll show how the projection is done first. So we will bring in that dotted line. So from B, a perpendicular drop goes on towards the normal, and similarly we'll have from A a perpendicular drop onto the normal. And what that does, now the vector AB will have the same size as this particular segment, which will become the distance between the two lines. And it is the shortest distance because that segment is perpendicular to L1 and L2. Now we've learned before how to find the projection of a vector onto another, and so we will go efficiently through these rules and formulae. So the first thing we're going to use is the distance formula as the magnitude of the projection, because we know that the projection of a vector onto another is a vector. So we need the magnitude of that projection, which guarantees a positive outcome as well. Now the projection formula of vector AB onto the normal n, which will give us that distance, is the magnitude, it's the absolute value of the dot product, since the dot product is actually a scalar quantity, so there's no point of saying the magnitude of the dot product. So it's just an absolute value because the dot product could come out negative. And dividing that by the magnitude of the normal vector, we can find first the vector AB. The vector AB is OB minus OA, and we've done that as well before. You subtract the point B, which is on line 1, minus the position vector technically of A, which is on line 2. We would get the vector AB a 9, 4, and we need to find a normal, not the normal. So to find a normal, all we need to make sure is the dot product between the normal or a normal and the direction vector of one of these two lines, since they're parallel, has to be 0. So the normal dot the direction vector is 0. That guarantees that the normal will be perpendicular to the direction vector. And so the normal here is a scalar multiple of 4, 1. And if we notice, if I take 4, 1 and I do a dot product with the 1, negative 4, dot product of algebraic vectors, you multiply x to x plus y to y, and you add them and you should get 0. So 4 by 1 is 4, and 1 by negative 4 is negative 4, so 4 minus 4 is 0. Now that we found the vector AB and the normal vector, we are able to find the distance, and the distance will be the absolute value of the dot product divided by the magnitude of the normal. And in that scenario, we're going to get 40 over root 17. You can feel free to rationalize the denominator, so it'll be 40 root 17 over 17 units. Now, that would be the case 1, two parallel lines in 2D. If we are to go to two parallel lines in 3D, as we will see in this page, the scenario is entirely different. So now we have 3D lines, which means we have an x, y, and a z component, and our two lines are still parallel. But since the two parallel lines in 3D, there is no way to guarantee that a random normal vector chosen for one line will also intersect the second line as well. So as in the case of 2D lines, we saw that before, the normal for one intersected the other, and it was right as well to it, right angles. In a 3D scenario, the lines are not necessarily in the same plane. As a result, we cannot project a vector AB onto a particular normal. So that is why what we will do, we'll find a creative way to find the distance between two parallel lines in 3D. So we will actually draw a parallelogram between those two parallel lines, and technically we will find the height of that parallelogram. So that's how it will begin. We'll bring in the vector AB, which is similar to the previous scenario in 2D lines. Point A is on line 2, point B is on line 1. Bring in that here. Then we're going to bring in the direction vector for line 2, and I will set them up tail to tail. So now I have the vector that's formed by a point on line 2 and a point on line 1, and the direction vector of line 2. Now these two vectors are going to be able to create a parallelogram between them. And I will extend this to help you see the parallelogram that will be formed, which will make it easier for us to think about how to find the height of this parallelogram, which will become the distance between the two lines. So now I'm going to bring in that segment that is perpendicular to both. It's perpendicular to line 1 and it is perpendicular to line 2, but in the same time it is the height of that parallelogram. And so now technically the exercise changed to finding the height of a parallelogram rather than the distance between two parallel lines. Now we know before previous knowledge that we can use here, we know the area for a parallelogram, and that drawing here is a parallelogram as a subscript, so area of a parallelogram, it is base times height. And the height of a parallelogram is nothing but the area divided by the base. Simple rearrangement. Now the question is, in this parallelogram we know the base. The base is the magnitude of the direction vector. But the problem is I don't know the area of that parallelogram. So that's the height, that's the base, and I have everything but the area now. To find the area of a parallelogram, we are able to use a previous formula that we learned and proved, which is that the area of a parallelogram is the magnitude of the cross product of two vectors. So the area of any parallelogram is the magnitude of the cross product of any two vectors you're using. And at this stage, all we need to do now is determine our vector AB, which is again OB minus OA. We know the point B is on line 1, so that is point B, and that is point A. If we do our subtraction of the position vectors, we'll get 943 for AB. And vector D2 is already available for us. It is the 2, negative 8, 6. Now we're going to rearrange. So we have the height is technically, instead of area over base, we're writing that magnitude of the cross product between AB and D2, the two vectors that form the parallelogram, divided by the magnitude of the base, which is the magnitude of vector D2. I'm going to show these right away, so you have in front of you, I'm finding them, but you can test it yourself as well. This is previous knowledge, no need to prove it again and again. So AB, vector B cross the vector D2, you're going to get the given vector here, 48, negative 80. And now we're going to determine its magnitude. So the square root of x squared plus y squared plus z squared. And that is a square root of 11,008. Similarly, we need the magnitude of D2, which is the square root of 2 squared and negative 8 squared and 6 squared, and that's a 104. And finally, we're going to find the height by dividing the magnitude of the area, a magnitude of the cross product, which is the area, divided by the magnitude of the base, which is the direction vector 2. And there we go, we have h equals 10.29. Now, you could also show the outcomes on GeoGebra, and that is something we can practice in class, how to check your answers using GeoGebra. In GeoGebra, you'll be able to input just the lines and ask GeoGebra to find the distance, and it will find automatically the distance. So I did take the liberty of checking that as well for myself before I did the video, but that is something we can discuss again in class. Okay, I hope you learned about the distance between two parallel lines, and feel free to stop the video and look at every calculation that I did on your own. The video is meant for being short and not long, so you can stop and pause and work, and in this way you're more active rather than passive. Okay, bye bye.